Here's the solution to 14.89. We have a toy car that's propelled by water that squirts from an internal tank at a constant 6 feet per second relative to the car. The weight of the empty car is 0.4 pounds and it holds 2 pounds of water. Neglecting other tangential forces determine the top speed of the car. So what we're given is a relative velocity u equals 6 feet per second. So it's a magnitude right here. Notice theta is equal to 20 degrees. The weight of the car is 0.4 pounds. The weight of the water is 2 pounds. We're going to look at conservation of momentum in the x direction since there's no external forces acting on the system in the x direction. And so what we have here to start off with is we're going to look at momentum at some time t. So that's going to be the total mass of your system right here, minus the q, which is the flow rate of the water. This is a dm/dt type of term, times time. So if we know the rate at which water is expelled, then we multiply times time and we get the amount of water that's gone. So this is the thing, this is the weight of the car, mass of the car, and the water it contains at some time t. Multiply times v and you got your velocity. All right, and then later on, after a little delta t of time has passed, we have that same expression right there occurring again, except t is now increased by delta t. And then v is increased by delta v. And then we have the delta m of mass that's been expelled during that delta t of time. Well, that's q times delta t times the velocity of the exhaust in the x direction. So that's exhausted water right there. So the velocity of the exhaust is the relative velocity plus the velocity of the car. Or the relative velocity is the velocity of the exhaust minus the velocity of the car. So anyway, the x part of this equation is VEX. The x part of the u is minus u cosine theta. And then the x part of v is just v. So what we're going to do next is to expand all these terms. So if you expand the right-hand side out, you'll get this right here on the, the left-hand side. If you expand it out, you'll get this right here. And if you expand the right-hand side out, you'll get all of this over here, including when you do q delta t times the minus u cosine theta. That's right there. And then q delta t times the v, and that's that term right there. Well, you can see that several terms cancel out. And basically, you're left to the equation of mc mass of the car times dv dt plus mass of water dv dt minus qt dv dt minus qu cosine theta. So if you get the dv dt terms together, you got this right here. And then the other term is going to be qu cosine theta when we take it to the other side of the equation. So to separate out your variables, you'll have the dv right here. The dt will go to the other side with the qu cosine theta. And you'll divide through by the mc plus m water minus qt. Well, just make note, this is a constant right here. This is the 0.4 pounds plus 2, so that's 2.4 pounds altogether, minus qt. Well, when you integrate this, the limits just start out with 0 velocity, 0 to v. You'll get v on the left-hand side. And on the right-hand side, you'll get this log function right here, taken from the limits 0 to t. You'll notice minus sign is appearing out here because when you take the derivative of this right here with respect to time, you're going to end up with a minus q. That'll change that into a plus q then, right there. So what we're going to do here is we're going to take care of the minus sign by flipping the limits and having u cosine theta out there. So it's a log of, when we plug 0 in here, we're going to get mc plus mw, that term right there. And then when we look at the time plugged in, we're going to get this right here. But now we're looking at the total time that it takes to expel all the water. And so that q times t is equal to m sub w. So this term right here is 0. And so what we end up with is a log of mc plus mw over mc, or weight c plus weight w over weight c. When you plug in your numbers, you'll get 10.10 feet per second, and it's to the right.